For the same problem, besides forward-backward procedure, there's an alternative approach, which is called a Viterbi algorithm. You can go through this equation yourself, but we'll just show you something very simple. Again, using this example. So instead of keeping track of alpha and beta numbers, here we're using a delta number and a psi number. So the delta keep track of the maximum probability to use a fair coin, or to use the particular coin in order to get to this point. The psi is a pointer to keep track of how I got here. So you can, I'll show you how to do this. So initially, the initial probability is we calculate this delta number, which is here for the delta 1 using a fair coin would be initially I have to pick the fair coin, so that's the initial probability, multiplied by the emission probability of using a fair coin to get ahead. And so these two multiply together, you'll get this delta number. And we also look at the delta for bias coin, which is you pick this coin to start with, you emit ahead based on the bias coin using the emission probability. So you keep track of this delta number. And then we start to go through the Markov chain. At every point, remember for forward-backward procedure, we calculate the sum. But for Viterbi algorithm, we keep track of, we only use the maximum of the two numbers, or in this situation, we only have two paths, so you just use the bigger number. But in some situation, you might have multiple states, then we pick the maximum number to use. So, so let's say if we want to calculate the probability of, or not probability, we want to look at this delta number for the second coin being a fair coin. We say, well, if this is a fair coin, what are the chances that there's one possibility that the previous coin was already a fair coin, and we inherit this delta number, and then transition from the fair coin to a fair coin. Alternatively, we come from the bias coin here in order to get all the coin flips before that. And we transition from the bias coin to the fair coin. And so it's this delta number multiplied by this transition probability. And at this point, instead of summing them up, we make a comparison. We check which one is the biggest. And in this case, let's just say this pass gave me a bigger number. Then my psi is a pointer to say, okay, actually, I'm adopting this particular path in order to use this fair coin. And then at this fair coin, so basically you will only use this previous delta number multiplied by this particular transition probability, and then multiply by the emission probability from the fair coin to emit a tail. And then you keep track of this new delta number here. And same thing here, if we calculate compare the probability of getting here from the fair coin, that will be this delta number multiplied by the transition probability from fair to bias. Compare with this, if we use a bias coin in here and transition from bias to bias, so this delta number multiplied by this transition probability, we again do a comparison, and we pick the bigger one and use that number to multiply by the transition probability of a bias coin to give out a tail. And the pointer here, the psi, will keep track of the path to get here. And so we do this at every step. We say, well, next one, again, we inherit this number multiplied by the transition probability and compare with if the previous coin is a bias coin and multiply by the transition probability. We make a comparison. basically at every step, we always pick the winner. Instead of summing them up, we always pick the winner. And then we know at this point, from fair coin, we have to emit a tail. And alternatively, we try, not alternatively, we can also calculate the same delta parameter for the bias coin. It could come from a fair coin, or it could come from the bias coin. We pick a winner again, and at this point, we emit the tail, and so on. And so this is, again, a Markov chain. It also uses dynamic programming because at every step, we keep track of the delta number and we use it for the next calculation. And how does this terminate? So at the final termination, we just compare the two numbers at the very end, the two delta numbers at the end. And again, we pick the bigger number, or the maximum number. And supposedly the bias coin give us a better delta number. Then we just backtrack. We ask, in order to use the bias coin to get this, because we know this is giving us a higher probability, then we ask, how did we get here? Well, based on the psi to keep track of our path, we know, oh, okay, in order to get here, we took this path and the previous coin is biased. And then the pointer tells us that the previous coin is fair, and then the previous coin is biased. And so we will have the path as well. And so compared to so at the end, you output your prediction, which is, bias, fair, bias, biased. And this gives you another solution to the second problem, which is the path. The difference between Viterbi and forward-backward procedure is that, remember we mentioned that in order to see this particular coin flip, there are a gazillion different ways you could use the coins. There's different path. Every path will have a probability of giving you this head, tail, tail, head coin flip. And Viterbi algorithm will find the path that give you the highest probability of flipping out this particular string of coins. And because at every step, you pick the winner. And at every very end, you pick the ultimate winner and you backtrack. And you make sure that, because this is the ultimate winner, at every step, again, you pick the winner. Therefore, this is the correct path that gave you the highest probability among all the paths to give out this particular coin flip. In most of the locations, you might see that the Viterbi algorithm and forward-backward algorithm give you very similar predictions, but occasionally there could be something that are slightly different. For example, sometimes the forward-backward algorithm, remember, it maximizes the overall at every state, the final states being correctly predicted, whereas Viterbi give you the path that have the highest probability. Sometimes a forward-backward algorithm might give you a path that based on your transition probability could never happen. But Viterbi algorithm will always give you a plausible path. And so most of the time you will see that they give you similar predictions, but occasionally there might be some small differences. Oops.